Okay, last time we introduced hydration. So, well, actually, we started with hydrohalogenation. That's the addition of HCl, HBr, HI across a double bond. There's Markovnikov and anti-Markovnikov. So Markovnikov, the halogen or the bigger functional group, adds to the more substituted carbon. And then in anti-Markovnikov addition, it adds to the less substituted carbon. Then hydration, instead of HBr or HCl, it's HOH, just water. And the first set of reagents involves either using water with catalytic sulfuric acid, or you can write it as H3O plus, which is really the same thing. Okay, that's Markovnikov hydration. So the OH goes on the more substituted carbon. And then we talked about how that's in equilibrium with the opposite process, which is dehydration. And that's what we did in lab. And you can control that by varying the concentration of your acid that you use in the hydration or dehydration reaction. Now, let's look at a mechanism for this reaction. So I'm going to write it as H3O plus because it's going to make it much easier to show movement of electrons and atoms just using that. Okay, so this is going to start out just like hydrohalogenation. Okay, we're going to have a proton transfer as the first step. The pi bond is going to grab a hydrogen. And then, right, in the hydrohalogenation case, this hydrogen was attached to the bromine or whatever. But here it's attached to a water molecule, and that's okay. And now the question is, okay, which carbon is the hydrogen going to end up attached to? One of those two pink ones. So this is Markovnikov addition, which means the OH, which eventually is going to get added, ends up on the more substituted carbon. So the hydrogen ends up on the less substituted carbon. Okay, so that means, okay, the less substituted carbon is on the right. And so that's where our hydrogen is going to be added. Okay, the other carbon now has a positive charge. Okay, better to form that secondary carbocation than the primary carbocation that would be formed if we'd used that carbon with the C plus. So we've made a carbocation. What can always happen? Rearrangement. And look at us, we've got a secondary carbocation right next to a tertiary carbon with a hydrogen on it. And so we can rearrange, do a hydride shift. And now we have a tertiary carbocation. Okay, so now our carbocation is rearranged. we can have nucleophilic attack. And the nucleophile, instead of being OH, is going to be OH2, so water. And this is the water molecule that was formed when that H2O group left during the proton transfer. So we're going to make a bond to the carbocation. And remembering that when we're making this oxygen carbon bond, the two hydrogens on the oxygen stay with it. Okay, and that gives us an O plus. And now all we have to do is another proton transfer so that our ending molecule is neutral. And we can just use another molecule of water to take that proton away from the oxygen. And that becomes our product. We can erase these explicit hydrogens. And there's our addition product. Of course, noticing that the two carbons that used to be part of the alkene, right, neither of those carbons has the OH substituent on it because we had a carbocation rearrangement. Okay. Obviously, it would be nice if we didn't have to worry about the carbocation rearrangement, and there is a way to do that. And we're going to use a reaction called oxymercuration demercuration, or just oxymercuration. So let's use our same starting material. We know that if we add just H3O plus, we're going to get this rearranged product. But maybe we would really like to have just regular Markovnikov addition, where the OH adds to the most substituted carbon of the alkene and there's no rearrangement funny business. Okay, and this reaction here is what we're going to do. Oh, I have my segmented eraser. There we go. Okay, so for oxymercuration, demercuration, we have to use it's really two steps, but we write them together usually.
Is it instantaneous like the SP, like the two reactions or no?
No, so it's almost like doing two separate reactions completely. So the first reaction we use mercury to acetate and water. That's the oxymercuration part. And then we use sodium borohydride in ABH4 in a second step. Essentially, that's the demercuration part. It gets rid of the mercury. Okay, and that does what we want it to do, gives us Markovnikov addition. Cross the double bond without the carbocation rearrangement. Unsurprisingly, there's no carbocation formed in this process. We're not going to talk about the mechanism. So, if we have a molecule, I don't know, like this, where, okay, if we do, right, the first step of the regular hydration with H3O plus, do the first step, and that's going to give us the hydrogen on, we don't have a less substituted carbon here. Let's do this. Give us a hydrogen on the less substituted carbon and carbocation there. Okay, this is going back to the stuff we just did. If we do something like this, we are not concerned about a carbocation rearrangement because we already have a tertiary C+, okay, and there's no rearrangement that can happen. So in a case like this, you can use either H3O plus or oxymercuration, demercuration, and you will get the same result. Now, would you rather use some dilute acid or salts of mercury if you were doing this reaction in the lab? Do you want to work with soluble mercury salts? Uh-uh. Um, Toxic. Yeah, mercury metal isn't very toxic, but mercury 2 salts, um, so sort of like what's found in fish and stuff, if you eat too much of it, is toxic. So yes,
Some fish, how the toxic, is their bodies like tolerant to it?
it's mostly predator fish like tuna and stuff that eat the smaller fish, and so the mercury that ends up in the water from pollution, the little like the krill eat that, and then the slightly bigger fish eat them, and then so on and so forth up the food chain. And so like the large fish concentrate mercury in their bodies. Um, and they do that with other stuff, other toxins too, but mercury is like the famous one that everybody is scared of, and for good reason. Anyway, um, yeah, so if you have a choice, you want to use the regular acid method, and the mercury process is generally reserved for when you specifically need to avoid a carbocation rearrangement. I won't mark you wrong if you use oxymercuration when it's not necessary, but might cost you a few hours of your life um, inhaling mercury vapors or whatever. Anyway, so H3O plus is still sort of the default one for this. Okay, so both of those, the acid method and the mercury method, those both give the Markovnikov product. Okay. So we would also like a method that gives the anti-Markovnikov product. And there is one. And this process is called hydroboration. So we're going to use boron instead of mercury. So we can use our same alkene. And the conditions, this is another one that's two steps that are kind of written together. BH3THF, that dot in the middle is like a math multiplication dot. Followed in a separate step by hydrogen peroxide and sodium hydroxide. If you remember, for hydrohalogenation, the way we got anti-Markovnikov was by using peroxide. And look at that, we're using peroxide again to get anti-Markovnikov. Not a coincidence.
What did you say two twelve?
I did. I'm going to get there. Good question, though. So anti-Markovnikov, that means the OH goes there and the hydrogen there. Okay, so what's this BH3THF thing? Well, BH3, that's fairly self-explanatory. That's just borane. Borane by itself is extreme. It should be trigonal planar, but I'm going to draw more stuff. Borane is really reactive by itself, and so you can't buy it in a bottle. What you have to do is get it as a solution dissolved in THF, which is tetrahydrofuran, an oxygen in a five-membered ring. This is a really common, fairly cheap solvent in organic chemistry. And this whole thing here is what we call BH3THF. And it's a liquid dissolved in THF, and you just pipette it or syringe it into your solution. Okay, the important thing here is the boron atom, though. So anti-Markovnikov.
So that single bond connection.
That's an arrow. It's a special kind of bond. It's kind of like a single bond. Although if it was a single bond, we'd have to give the boron a negative charge and the oxygen a positive charge. When we use these kind of bonds, it doesn't really do that. I'm not going to ask you the structure of that. I just want you to have seen it. Essentially, one of the lone pairs on the oxygen is sort of kind of flirting with the boron. Okay. All you need to know is the main reaction stuff. All right, so let's make a little summary of hydration reactions. So if we want Markovnikov addition, and we are okay with having a possible carbocation rearrangement, or we want one to occur, then we'll use acid. If we specifically want to avoid a carbocation rearrangement, we use oxymercuration demercuration. And if we want anti-Markovnikov addition, we use hydroboration. Okay, so 3 methods for hydrating alkenes. Okay, our next reaction is hydrogenation. Okay. Unsurprisingly, hydrogenation is addition of 2 hydrogens. Okay, so this is just the addition of hydrogen gas, essentially, across the double bond. Okay, and the conditions for this, pretty easy. We're literally just going to use hydrogen from a hydrogen cylinder. And we also need a metal catalyst of some sort. So this can be, all right, this is palladium. Can also use platinum. Nickel in some cases, a special form of nickel. And this is going to add a hydrogen to each of our, it's just going to get rid of the double bond, basically. So we could write it just like this, because it's just an alkane. But we can also be a little bit more specific and say that, come on. Both of the hydrogens in this particular process end up on the same side of the alkene. Well, it's not an alkene anymore. So both of the hydrogens are added to the same side of the molecule. There is an explanation for this. So what happens is you, well, okay, so the palladium or platinum or nickel metal catalyst, well, this a little different from the nickel, but the metal catalyst you buy as basically carbon charcoal powder that's been coated with a very small amount of these expensive rare metals. You add that to your reaction mixture, and so you get right, you just have these metal particles floating around. They're not dissolved, they're just floating around. Okay, and then on the surface, when you add the hydrogen gas in, usually you have to do it at higher pressure, often very, very high pressure. But when you do that, you end up with hydrogens basically attached to the surface of the metal particles. Okay, and when the alkene comes in, right, the bond that ends up getting formed is always on the same, the 2 bonds are on the same side of the molecule because both of the hydrogens are attached to the metal catalyst when they are installed. That's the least mechanism-y kind of mechanism that you can possibly draw, but that's basically how it works. There are going to be several, in fact, most of the other reactions we're going to talk about today have some sort of stereoselectivity like this. So this is type of stereoselectivity. And generally speaking, if you've got two things on the same side of the molecule, that means that they were kind of held in position by the same thing when they were put onto the molecule, right? Otherwise, the opposite case would be something more like an SN2 reaction, which we're going to see well, pretty much next. But anyway, so catalytic hydrogenation gives you syn addition when you use hydrogen gas and a palladium or platinum catalyst. You can also get anti-addition by using a different catalyst. Okay, it's called Wilkinson's catalyst. It also uses a rare transition metal, but it's more complicated. It's got other things going on. And this will give you anti-addition. Actually, really, I should say. So it doesn't matter which way you draw the wedge in the dash or which one you pick, because both of those. Okay, again, here's me being not very technical. Really, it's and. Okay, you get both of these. But I really only care that you draw one of them and that you've drawn uh, the anti-configuration of the two hydrogens. Okay, and for many cases, it's not going to matter. Actually, in this case, it shouldn't matter because the hydrogen on the right is not on a stereocenter. But
How do you ask that question? How do I know, just saying on the left side that I need to use Wilkinson's catalyst, or would you tell us?
so if I give you just this with no stereochemistry indicated, is that what you're asking? It doesn't matter. You would use in real life, you would just use palladium because it's cheaper, but for our purposes, either one works fine. Yeah, so if you didn't hear what he asked, um, if there's no stereoselectivity in the reaction, which one do you use? And the answer is either one. That's as complicated as hydrogenation gets, pretty much. Okay, so next is halogenation. Okay, this differs from hydrohalogenation, actually in quite a few ways. So this, instead of being the addition of HX, it's the addition of two halogens. So diatomic chlorine, bromine, or iodine. And these are the reagents that we're going to end up using for halogenation. For our example molecule, I'm going to draw cyclopentene kind of on its, I'm looking at it kind of on its side. okay, because we're going to see the 3D consequence of this reaction. If we add to this a halogen like bromine, okay, we're going to add the two bromines across the double bond.
I'm drawn on that.
The mechanism I'm going to show you is kind of easier to visualize when you draw it on the side like that. But so halogenation like this is anti. And the mechanism explains why that is. It's a bit of a bizarre mechanism, but okay. So we've got our alkene, and then our reagent is diatomic halogen. Okay, this first step is weird, very weird, and it's got three arrows. So two of them are nucleophilic attack arrows, and one of them is a loss of a leaving group arrow. So double nucleophilic attack plus loss of a leaving group. Okay, so the first arrow is going to go from the pi bond to one of the bromine atoms. Which type is that?
Technically, there's a bit clear there.
Yeah, it's nucleophilic attack. Okay. At the same time, one of the lone pairs on that same bromine is going to perform nucleophilic attack on one of the carbons of the alkene. Okay, so the first arrow is starting in the middle of the alkene from the pi bond, and the second arrow is going from a lone pair on the bromine to one of the carbons. Okay, and then the final arrow is the loss of a leaving group, and the leaving group is this other bromine. Is just going to go away. Now, spoiler alert, the bond, okay, so the bond that's formed by this top arrow, the second one we drew, okay, that's going to be a bond between bromine and this carbon. Okay, that's pretty clear. But what about the first arrow? Okay, it ends at the bromine, so it's definitely going to be a bond to the bromine, but which carbon is it coming from? The answer is this one. Okay, so we're going to make that bond to the bromine. Okay, so what does the product of this look like? Um,
VR only, yeah.
so, yeah, bizarre. Okay, we've made a three-membered ring. Where the bromine is attached to both of the carbons that were part of the alkene. We've also got the Br minus that got kicked off. And it's floating around. Okay, our charges have been conserved. The first bromine has a positive charge, right? You hardly ever see halogens with two bonds. That's normally like super illegal. Okay, but in this case, it does happen for a very short time. That gives it a positive charge, and then the Br minus, of course, has a negative charge. This weird ion has a name. Bromonium ion, so that's our three-membered ring with the Br plus in it. Okay, the next step is basically an SN2 reaction. So what is our nucleophile going to be? The floating bromine. And the electrophile is going to be, doesn't really look like it, but an alkyl halide. Okay, so this carbon-bromine bond, we can consider that just like an alkyl halide, all right? And so bromine attacks from the opposite side. Well, the floating bromine attacks from the opposite side that the bromonium bromine is on. And then we have loss of a leaving group. SN2 reactions are characterized by inversion of stereochemistry. So the bromonium bromine is at the top. Okay, if we're talking about stereochemistry at, what did I do? Oh, I got rid of my leaving group arrow. Sorry. So if we're talking about the pink carbon having inversion of stereochemistry, at the beginning of the reaction, the bromine was at the top, and now at the end of the reaction, the bromine, which is now a different bromine atom we're talking about, is now at the bottom. Okay, so that ends up looking like there's the bromine that was part of the bromonium ion, which was our leaving group. Okay, it's still got a bond to the left carbon, so it's still hanging on. All right, and then try that again. Nope. Our nucleophile bromine, our floating bromine, is now attached to the bottom of the pink carbon. And that's what gives us anti-addition. Okay, so the key to that anti-addition is basically an SN2 mechanism.
That bromonium ion, that's so drawn as a side here,
As what?
as a side here.
Yeah, good point. So in this case, I'll draw a top view in a second. What you can do is we're trying to really make sure that people can see the 3D-ness of it, is to take these bonds that are closest to you and make them really thick, kind of like wedges. Okay. And so now, right, it looks like those are coming towards you. In reality, the bromonium ion is actually leaning back a little bit, but don't worry about that. Okay, so what does this actually look like in practice? Okay, so we'll use cyclohexene because it's easier to draw. And how about we use chlorine instead? Okay. The chlorine equivalent is a chloronium ion, if you really want. Okay, so this is sort of the intermediate, and the way we would draw that is like that. So there's your top view. Okay, the ring is somewhat flat. It's actually a chair, but whatever. And then the chlorine is either coming up toward us or going back away from us. So if you're drawing it as a side view, and you want to show stereochemistry, you should draw double wedges or double hashes. Double wedges is more common, but doesn't matter. Okay, and then if you're really lazy and you don't want to show any stereochemistry, then you are welcome to just draw that. There's not really a way to do syn halogenation. I mean, you can, you have to combine two different hydrohalogenation reactions. But when we get into doing synthesis, I think there's an example of that in the homework, actually. Okay, very similar to this mechanism is, when I say very similar, I mean like basically identical. Is the formation of a halohydrin. Okay, halo meaning halogen and hydrogen meaning water. Okay, and instead of two halogens, we're going to add a halogen and a hydroxyl group. In this case, you can't add bromine hydroxide, that doesn't really exist, into your reaction. And so what we end up doing is halogenation conditions with some water present. Okay. So what that does gives us our bromonium ion, and all that happens in the same fashion. The only difference is the nucleophile that comes in and attacks from the bottom in that SN2 reaction is water, which ends up being hydroxide. Okay, so that's the product, and I'll show you the key mechanistic step. Right, and so this proceeds just like the one above. Do our SN2. There we go. And then the next step, proton transfer to get rid of the extra hydrogen. And then we get to our product, which is called a halohydrin, right? And this is also anti-addition.
Halohydrin?
Yep, halohydrin.
Another question.
Yes. Yes, and so one of the common side products of this reaction is the product with two bromines on it. Because when you've got this bromonium ion, yeah, you still got your Br minus that had to come off from the original Br2 molecule. And so who's to say that the bromine can't attack in the SN2 reaction as well? And it does, but water actually does it faster in this case. This was kind of weird, but
With exception, those two like always happen at the same time.
Hmm?
The one, halogen one. Oh.
halohydrin. So if you have water, you'll get the halohydrin. If you don't have water, you'll get the fully halogenated product. In fact, is more of an issue when you're trying to do the complete halogenation with two bromines. If you've got any water in your reaction, you're going to get a lot of the halohydrin side product, which is annoying, but okay. Next reaction, dihydroxylation, okay, addition of two OH groups, which is essentially the equivalent of hydrogen peroxide. So the overall scheme for this is start with our alkene. Then we add a peroxy acid. Okay, as a reminder, our CO2H is a carboxylic acid. If we add an additional oxygen into the mix, we get a peroxy acid. Okay, this gives us another three-membered ring, this time with oxygen. That's called an epoxide. Okay, this is the second part of Lab 7. In fact, this exact reaction. Then if you treat an epoxide with acid, epoxides are pretty sensitive, so they react quickly. And for the same reason that the bromonium ion thing gives you anti-halogenation, the epoxide gives you anti-dihydroxylation. We won't draw the mechanism, but the reason's the same. Okay, and this part is the third half, the third half. I need to go to the math class. It's over on the other side. The third half of lab 7 is this, we call it a ring opening because we're opening the 3-membered ring. But anyway, okay, so that gives us anti-dihydroxylation. Now we should probably talk about this peroxy acid because it's pretty vague. That is, okay, R can be with anything. But maybe the most common peroxy acid and the one that we're going to use in lab is meta chloroperoxy benzoic acid, also known as MCPBA. Okay, so if it was just regular benzoic acid, it would look like this with an OH attached to the carbonyl. But for a peroxy acid, we're actually going to add an additional oxygen, right? That's that O3 in between. Okay, and it's metachloro, so that goes there. The key part of this molecule is the weak bond between the two oxygens. Okay, this is the same reason that hydrogen peroxide is reactive. But this is a common peroxy acid that's used. Okay, so using peroxy acid to make an epoxide, and then, well, the epoxide in itself can be a useful molecule, but generally its main use is to make the also. This kind of functional group is called a diol because it's a dialcohol. Anyway, so that gives us anti-dihydroxylation. Sometimes we'll want syn dihydroxylation. Unfortunately, this method is expensive and kind of dangerous, but it do be like that sometimes. So for syn dihydroxylation, the product is going to be either both OHs on a wedge or both OHs on hashes. For this particular molecule, these are identical, but other molecules, these might be diastereomers of each other. Okay, the reagents are catalytic osmium tetroxide. I would try to draw the toxic symbol, but I can't draw. Osmium being a platinum group metal is really expensive. It might be just about the most expensive platinum group metal, so it's more expensive than gold. And it's osmium tetroxide itself is really toxic. So it's a solid at room temperature, but it's volatile. So it's kind of in that way behaves like a gas because it evaporates really easily, and so you breathe it in and you get heavy metal poisoning and such. Okay, second step is SO3. Sodium bisulfite, mostly to neutralize the osmium tetroxide. So that's how we get SYN dihydroxylation. What I will say about the let's see, about this anti-dihydroxylation is it's not super necessary to draw out the epoxide intermediate. So what you might see people do is just write 1 and then 2. Okay, and that's fine. It's fine with me. It just leaves out the information that there is an epoxide made in between. Well, the first step makes an epoxide. The second step opens the epoxide to make the diol. And by the way, this goes for pretty much any multi-step reaction. Okay, as we start doing synthesis problems, I don't know, maybe you have a 4-step reaction, and what you could do is draw out the first step, product A or starting material A going to B, B going to C, then C going to D, and doing each of the reagents individually. That's more detailed and gives you more information about what's going on. But if you just want to get to the point, you can write the starting material, arrow, and then the product, and have 1, 2, 3, 4, 5, 6, 7, 8. Obviously, that gets ridiculous after a little while, but it's an abbreviated way to write it. And you're allowed to do that. That's okay.
Sounds like they're just frustrating if you, unless you're like a pro chemist.
Well, I am a pro. No, just kidding. But yeah, sometimes you'll see like 6 steps, and I'm like, oh God. Now I have to go in and be like, okay, this is gonna make this, and this can make this. Also, it depends on like this type of abbreviated writing is really good for what we call one pot reactions, which is where you're doing all of the reactions in one flask. And so you just add the first reagent, stir it, add the second reagent, and so on and so forth. And like then it's okay to put out all this, put everything abbreviated like this, because I don't care what happens. But if you have to do like a workup and isolate your product and get a percent yield and all that stuff, it's nice to have it written out. Anyway. Okay, questions on dihydroxylation? Got one more left. Okay, so this is the one that doesn't this is the one reaction that doesn't fit with all the others because um this is the only one that's not a type of addition reaction. All the others have been addition reactions. Okay, we basically open up the double bond and make a bond to one thing and a bond to another thing. This does not do that. But I wouldn't say it's harder. It's just weirder. Okay, so we start with an alkene. First, we treat it with ozone, O3, hence ozonolysis. And then with dimethyl sulfide, which you can write as Me2S, okay, because it's S with two methyl groups, or DMS, dimethyl sulfide. And this is really kind of interesting and weird. Okay, so there's a method for drawing the products here. So the first thing you want to do is draw the starting material, but make the alkene super long, like ridiculously long, like that. I swear, it's gonna make sense. Okay, so draw your alkene super stupid long, and then go in the middle and erase like that. So you still have some double bond left over on both sides, but you got space in the middle. And then put in an oxygen. That's it. That's literally it. Bruh. So, you're literally just cutting the molecule at the double bond and installing carbonyls in its place. Okay, so the way it's drawn here makes it super obvious to see where the two parts used to be connected. Okay, but you can also have the products drawn in a more kind of in a more standard form. Like that. Okay, the first product on the left is an aldehyde, and if you use this process to draw the products, you won't have that extra aldehyde hydrogen explicitly drawn, even though it's traditional to draw it. Okay, and so in the products in this the products on the very far right, we've drawn them more like we usually draw organic molecules, with the carbonyl sitting up like it's supposed to. And so right at this point, you got to go, okay, well, here's my starting materials. I'm going to cheat because I have the iPad, but okay, so we put the oxygens together like this. And there's our starting alkene. Which, let's see if I do it correctly. Yep, there we go. Another way to complicate this or these reactions is to use a ring. All right. But don't let that scare you. It does the same thing. So what we need to do is really,
Forward shopping ball there.
yeah, come on. You see what I'm trying to do? Oh, that's ugly. All right. Anyway, so elongate our double bond. erase, put in your oxygens. That is a perfectly acceptable answer, as ugly as it looks.
Big one thing.
1, 2, 3, 4, 5, 6. Okay, or more traditionally, might see it drawn out like that. That makes it a little bit harder to wrap your brain around doing the reverse. For example, if I asked you to synthesize that molecule through an ozonolysis reaction or through any reaction, right? You'll have to see that, okay, those two carbonyls can come and sort of click together, and that gives us a six-membered ring. And of course, at that point, counting the carbons, 1, 2, 3, 4, 5, 6 is pretty important. Questions on ozonolysis? Really useful reaction. Actually, oh, hang on. There's one other case I should show you where trick questions are liable to come up. Nope. Something like this. Okay. How many organic products do we get from this reaction?
Stretch up the middle, right? And you can put that into.
Yep. So we're going to get this and that. What's the relationship between those two molecules? They're the same. Okay. So this reaction actually gives you two equivalents of that ketone. Again, it's not wrong if you draw it the way I originally did. But if I asked you, how many products does that give you? The answer is just one. This can be useful, right? You can, if you, if you just need this aldehyde, okay, and you have this starting material, okay, you're gonna make some acetone, but right, you're wasting all of that. We call this atom economy. You're wasting those atoms. You're just throwing them out. And if you have a case like the last example, we have basically perfect atom economy here because for the carbons, because all of the carbon atoms have been turned into the desired product. But that's a story for another day. All right. Next time we'll talk about synthesis and do a bunch of practice. No, I don't remember it. It's